Hey everybody, welcome to a new video in the Generative Music AI course. In the previous lecture, we saw how we can implement a cellular automaton to generate drum patterns. Today, we're going to be looking at a completely new algorithm for music generation. That is genetic algorithms. Here we have the menu for today's lecture. First, we're going to take a look at the intuition behind genetic algorithms. Then we're going to dive deeper and see a formalization of these algorithms. Then we're going to be moving into the music generation sphere and see how we can use genetic algorithms to generate music. And finally, we're going to be looking at pros and cons of genetic algorithms for generating music. Let's dive into it. So, what are genetic algorithms? In a nutshell, we can say that genetic algorithms are optimization techniques inspired by the process of natural selection. It is important that we understand this evolutionary process of natural selection well in the biological sphere, because this is going to be instrumental to understand genetic algorithms. So let's take a look at natural selection first. In nature, we have species with a lot of different individuals, and different individuals are going to exhibit variations in certain traits, like for example, color, size, shape, height. The problem is that in nature there are limited resources, for example for food or shelter, and this finite number of resources leads to a struggle for survival. Those individuals who have advantageous traits for a certain environment, in other words the fittest individuals, tend to survive and reproduce more, and when this happens, these traits get passed on to the next generations. Over many generations, what this leads to is a process of adaptation and evolution of the species, because the traits that are the most advantageous are going to replace those traits that are the least advantageous. And this is natural selection for you in a nutshell. And as old Uncle Charles Darwin would say, this is the survival of the fittest. It turns out oftentimes that computer scientists use things that come from nature in order to solve computational problems. We know that natural selection optimizes living beings, so why don't we use a similar process for optimizing our problems? These are problems where you have a large search space and you want to optimize the solutions for those problems. And that's how we get to genetic algorithms. We basically take the concept behind natural selection and we simulate it with a computer program. Now, let's take a look at the core idea of genetic algorithms. And it goes like this: solutions evolve over generations to optimize a specific objective. Now, let me try to map this computational idea into natural selection, into a biological idea. So, solutions are the equivalent of the individual animals. We have a population of animals, in the case animals or plants, of course, in the case of biology. In the case of computer science, we have a population of possible solutions. They evolve over generations. In other words, they reproduce. We have iterations, and at each iteration we have a new generation. Finally, to optimize a specific objective, and this is the survival of the fittest. We have a sort of fitness function, and we have fitness in biology as well, and that is the environment that basically indirectly tells us like what works and what doesn't work, and only the fittest tends to survive. And we do the same thing also for genetic algorithm. Let's move on and take a look at the different applications we can use genetic algorithms for beyond music generation. And these algorithms have been used for a gazillion different use cases. Like for example, to design things that have to do with the aerospace industry, for routing, networking problems, solving inventory management, or even for optimization of parameters for machine learning. Genetic algorithms work really well for fine-tuning of those ML parameters. Genetic algorithms have been used for financial portfolio optimization. Genetic algorithms have also been used for DNA sequence alignment or protein prediction, for anomaly detection and signal processing, and of course for art and music generation, as we'll see later in this video. Okay, now that we have a sort of high-level intuition of genetic algorithms, let's take a look at its formalization. We're going to go through all the different components that make up a genetic algorithm and the different so-called genetic operators. Okay, let's take a look at the key elements first. First thing, of course, is population. And as I introduced earlier, a population is just a set of candidate solutions, and these are the individuals. But of course, this is an abstract idea. So how do we actually implement those possible solutions? Well, we encode them in so-called chromosomes, and chromosomes are something like this. They're basically a vector, and you can think of a chromosome as a sort of vector with a lot of items, and each item, we can call it a gene, and each gene represents a particular feature of a certain solution or a problem. Say, for example, we want to design a table. Here I have a simplified chromosome for a table. We have number of legs, and that is a gene. We have the height in centimeters, for example, the width, the color, and potentially you can have 10 or 20 more of these singular individual genes. And here you have an example of a chromosome. So we have a table with 5 legs, quite unusual, but why not? Height is 80 centimeters, 90 centimeters is the width, and then the color is red. Okay, you get the idea. At the end of the day, we're basically dealing with a vector here with a lot of items that represent different things. So this is the so-called genetic information and how we encode a solution. Then, of course, we have a fitness function. The fitness function is a function that basically measures how effective, how fit a certain solution is. Beyond the key elements of genetic algorithms, we also have 3 genetic operators. These are used at every iteration of the genetic algorithm. The genetic operators are selection, crossover, also called recombination, and mutation. Let's dive into each one of them in isolation. Selection first. Okay, this is quite straightforward. What it does, it's simply choosing the fittest individuals for producing offspring, for producing the next generation. How does this work? Well, usually the likelihood of an individual being selected is usually proportional to its fitness. There are different strategies we can use to select parents for creating the next generation. These are some of them. Roulette wheel selection, that basically follows this idea that the likelihood of an individual being selected is proportional to how fit it is. Then we have tournament selection. This one is slightly different. Basically, the idea is that you randomly choose a subset of the population. Say you have 1,000 solutions. That's the whole population. You take 100 individuals randomly, and then there you prioritize by fittest. So basically, the fittest you are, the fitter you are, and then the more likely you are to get selected. And you repeat this process a number of times. And this actually allows for more diversity in the solutions so that you avoid having a convergence of the algorithm too soon, because you're always going to get like the best possible solutions there. Then we have rank selection. This one works like this. So you start by evaluating the fitness for all the solutions, and then you rank them from fittest to least fit. And basically what you do at that point is you use this ranking as a way of proportionally determining the likelihood of being chosen. It's the ranking itself, not the fitness. Okay, that is for selection. Now we have crossover or recombination. This is the process of creating a new offspring starting from 2 parents, and it works like this. So you combine the genetic information of 2 parents to produce a new offspring. So how does this work? Well, you basically do what happens in a biological situation where you have this sort of crossover of chromosomes that come from parents. Basically, you take like parts of the chromosomes from one parent and part of the chromosomes that come from the other parent, you mix them together and you get the offspring. There are different strategies for doing this recombination. The two most famous ones are 1-point crossover and 2-point crossover. Let me just show them real quick. So 1-point crossover, you have parent 1 and parent 2. You decide a point where you want to apply the recombination. In this case, like is at between like the second and the third gene, but it could be randomly chosen wherever you want, or you may have a criteria or a series of criteria for that. Okay, and then the offspring is basically the recombination of the first part, the first two genes, in this case, that come from parent 1, and the third and fourth gene that come from parent 2. And that's the offspring for you. Let's take a look at 2-point crossover. In this case, you take 2 points, not just 1, 2 points. And what you do is you take whatever come before the initial 2-point selection comes from parent 1, then you basically take the genes within the 2-point selection coming from parent 2, and then the rest of the chromosome comes from parent 1. The whole point of applying crossover is to create genetic diversity and generating new solutions. 1-point crossover is quite straightforward and it's simple to implement. 2-point crossover allows for more diversity and more exploration of the solution space. Finally, in terms of the genetic operators, we have mutation. With mutation, we introduce variation into the offspring genetic information, and we do that randomly. So a mutation is basically a random change that is made to parts of the genetic code of the offspring. Mutation is very handy because it prevents the algorithm from becoming too homogeneous too fast, and it also helps in exploring the solution space more. It is important to use a mutation rate that is quite low, because if it tends to be quite high, basically you're just doing random search because you're flipping all the genetic material randomly. So you have to do it, but do it cautiously using a low random rate. By now you should have a very good understanding of the different elements that make up a genetic algorithm and the key operators, genetic operators. Now let's move on and take a look at how a genetic algorithm works step by step. First, we have to initialize the population. We have to come up with individuals or possible solutions. We can do this completely randomly, or we may have some criteria for coming up with a solution. Then we start the actual iterations. The first step is to evaluate the fitness, and for this we use a fitness function. So now we have fitness for each of the individuals in the population. Then we apply selection. We select the parents which are going to generate the next generation, the offspring, through crossover. Then we apply mutation to the genetic makeup of the offspring. And finally, we do replace the population. We can do this in a number of different ways. We can completely remove the original, all the parents, and replace them with the offspring, with all the offspring, or we could keep a part of the parents and the offspring. There's a final thing we have to do, that is checking for the termination condition. For example, this could be whether we've gone through all the iterations that we wanted to go through. Say, for example, 1,000, 2,000 iterations, and these are all the different generations. And indeed, all of these steps in purple are the ones that we have within an iteration of the algorithm, and that's equivalent to a generation. And we loop through those again and again, again and again, until we reach all the number of generations that or iterations that we want to go through. Okay, that's the genetic algorithm step by step for you. Now, important question. What are genetic algorithms good for? Well, they tend to do quite well for all of those problems where traditional optimization techniques tend to fail. In particular, we're talking about search spaces that are large, complex, and potentially multimodal. They tend to do quite well with these problems because they have this balance between the diversity and adaptation. So they tend to adapt over time, but at the same time, if you use the right strategy for selection, for crossover and mutation, they can also avoid local optima and look for a lot of different solutions in the solution space, which is great for solving complex problems. Now, let's take all of these abstract ideas and concepts about genetic algorithms and use them for music generation. Here I'm going to give you a 3-step guide on how to use genetic algorithms for generating music. First of all, you have to encode musical elements as chromosomes. What are these musical elements? Are the usual parameters, like for example, melody, rhythm, or the whole composition, or a drum pattern. We have to find an encoding that works so that we can take all of these musical concepts and encoding them as a chromosome and using those chromosomes for running these genetic algorithms. Then we have to craft a music fitness function. We'll see how we can do this, but I have to admit that this is a tough process. And finally, you just run the algorithm. You, of course, have to design the algorithm in the sense that you have to decide what type of crossover to use, what type of selection, what type of mutation. But, I mean, the algorithm is the algorithm. The only musical stuff here is how you encode the musical information and crafting the right music fitness function for your musical use case. We can use genetic algorithms for generating all sorts of musical elements, like for example, melody, chord progressions, drum patterns, entire compositions, or even sounds through sound synthesis. Let me show you a few examples of how we can encode different musical elements as chromosomes. Let's take melody as an example. So the idea here is that for each gene, you basically have a note, and within each gene, you have information regarding that note, that is pitch and duration. Let's take, for example, the first gene here. So we have C4, C being the pitch for the octave, and dash 0.5. So basically, this is an 8 note. Okay, and in this case, we have D4 dash 1. So that's a D, octave 4, and that is a quarter note. This is a simple way of encoding melody as a genetic material. Of course, you can have different representations if you want. Now, let's take a look at chords encoding, for example. This one is also quite straightforward. We have one chord per gene. First gene, C minor, then D minor, D major, G minor, C major. That is a chord progression encoded as a chromosome. Sound synthesis. This one is particularly interesting, and I've played around with this quite a lot in my career. So basically what you do is you say you have a synthesizer, of course a modular synthesizer. A modular synthesizer is going to have a lot of different parameters. You can encode sound as different parameters that you have for that synthesizer. For example, let's take this simplified version of a sound. So the first gene is the cutoff frequency, and of course these are all normalized between 0 and 1, okay? All of these values in the genes. Reverb, so the amount of reverb, and 0.46, you can have information about the frequency of the first oscillator, the second oscillator, delay, and all the different parameters that make up your sound. And of course, like, this is a very simplified version of that. Potentially this chromosome could be could have like 100 genes or even 200 genes, but you get the idea. There's a clear mapping between each gene and one particular parameter of the synthesizer. So we've seen different examples of how we can encode different musical elements as chromosomes. Now let's take a look at a fitness function and understand what that is. So a fitness function evaluates the aesthetic value of a composition. It could be directly inferred from music theory, musicology. Basically, I have an idea of what a melody should sound like in a particular style, for example, and then I can come up with a series of criteria to evaluate that in a quantitative manner, but it can also be learned from data, especially the weights, as we'll see in a second, of the different criteria. Those could be determined using some very primordial form of machine learning. The problem with these musical fitness functions is that they are highly subjective, because we really don't know what is a good melody, what is a good composition. So they're really complex to come up with. They're really stylistic dependent, and they really depend on the person who's crafting that fitness function. Let's take a look at an example of a fitness function for melody generation. So we can come up with a linear combination that accounts for multiple criteria. I call this criteria scale conformity, melodic contour, rhythmic variation, dissonance resolution. Let me give you an idea what I have in mind here. So, scale conformity, whether the notes that you have in a melody are parts of a scale. So that is like an important thing to have in order to have like a good melody. Melodic contour, basically here we take a look at the overall contour of the melody, and also the fact that the melody tends to work perhaps in small steps mainly rather than leaps. Okay, then we have rhythmic variation. We want some level of rhythmic variation here and balance between variation of rhythm as well as like homogeneity. And finally, whenever we have a dissonance, we want to resolve it. Okay, so these are some criteria, and of course I would have to quantify them. I need to write functions that quantify them once I have the chromosome, so that we can analyze the chromosome through all of these functions and getting numbers back. Okay, so once I have all of those, then I can create a linear combination where I'm going to have these weights, W1, W2, W3, so that I can weigh different criteria differently depending on how important I think they are, and I can sum all of them, and that is going to be the value of the fitness. That is a simple fitness function for melody generation. The problem though is that these fitness functions are extremely difficult to create, because as I said, this is a very subjective thing. It's a subjective aesthetic evaluation. So coming up with something that's consistent and that works is very difficult, and something that's also quantifiable, it's even more difficult. So there is a shortcut there, and these are what we call interactive genetic algorithms. In this case, we don't craft a fitness function, but rather we as human beings are the fitness function. And how does this work? Well, we can go back to the step-by-step process of a genetic algorithm, and so you'll see that most steps are the same, but in the case of an interactive genetic algorithm, what happens is that you have a human who provides the fitness to the algorithm directly. So there's no fitness function, it's not automatic, there's a human in the loop there. So the algorithm comes up with potential solutions, it offers the solutions to a human. It could be a composer, it could be a producer, music theorist, and this person decides what works well and what doesn't work well, and based off of that fitness information that the human provides, then the genetic algorithm continues running and creates offspring and new generations, and this goes on and on and on until we are satisfied with the result. This is a great approach and machine-human interaction for creative purposes. The only problem that you have there is that this can be very, very tiring and time consuming on the side of the human. Another important point, whenever you have an interactive genetic algorithm, it is extremely important that you have a nice user interface, because of course you want to present those results nicely, those potential solutions nicely to the user for evaluation. Okay, you guys, now we are at the point where we take a look at the strengths and limitations of genetic algorithms. So, what about the pros? Well, there are a lot of pros. First of all, genetic algorithms are super flexible. You can use it for whatever really music elements you want, for generating melodies, drum patterns, entire compositions. You really name it. Another great point about genetic algorithms is that you can use them to explore unconventional ideas, especially if you get very creative with the fitness function. You can really find completely new musical regions completely unexplored, and that's really, really cool. And I've used them extensively for melody generation and for sound synthesis, and I can assure you that they tend to work really, really well. And indeed, they tend to give actually good results, but of course the results are only as good as your ability to come up with strong fitness functions, or if you have a lot of patience, if you want to use interactive genetic algorithms. But as always with any algorithm in music generation or otherwise in any other computer science use case, there are limitations. And of course, we saw this already. Crafting this musical fitness function is extremely complex, and it is highly, highly subjective. Okay, folks, we are at the end of this lecture, and let's wrap it up by looking at the main points that we made throughout the video. First, genetic algorithms are optimization techniques inspired by natural selection, as we saw. A population of solutions evolve over generations to optimize a fitness function. While we run a genetic algorithm, we apply three main genetic operators, and these are selection, crossover, also called recombination, and mutation. The moment we want to use genetic algorithms for music generation, we have to do two things. First, we need to encode music elements as genetic material, in other words, as chromosomes, and two, we have to come up with a music fitness function, unless we decide to go the interactive genetic algorithm way, where you, as a human being, will be the active fitness function. Music fitness function is complex to design because understanding what makes good music and quantify that is very, very difficult indeed. But there's a great strength of this algorithm, that is that you can come up with unconventional musical ideas. Here you have it, guys, an introduction to genetic algorithms. I hope you've enjoyed this video. It's been quite dense, but hopefully everything was clear. If you have any comments, just let me know in the description box below. Next time is going to be Python time. We're going to implement a genetic algorithm that creates a chord progression accompaniment given a melody. Before you go, remember to smash the like button and to consider subscribing if you're not a subscriber of the Sound of AI channel. That's all for today. I'll see you next time. Take care for now.